Openstax, Contemporary Mathematics, Chapter 2, Section 6, De Morgan's Laws. Figure 212. De Morgan's laws were key to the rise of logical mathematical expression and helped serve as a bridge for the invention of the computer. Credit goes to them. It's a picture of the Golden Gate Bridge. Learning objectives. After completing this section, you should be able to 1. Use De Morgan's laws to negate conjunctions and disjunctions. 2. Construct the negation of a conditional statement. 3. Use truth tables to evaluate De Morgan's laws. The contributions to logic made by Augustus De Morgan and George Boole during the 19th century acted as a bridge to the development of computers, which may be the greatest invention of the 20th century. Boolean logic is the basis for computer science and digital electronics, and without it, the technological revolution of the late 20th and early 21st centuries, including the creation of computer chips, microprocessors, and the internet, would not have been possible. Every modern computer language uses Boolean logic statements which are translated into commands understood by the underlying electronic circuits, enabling computers to operate. But how did this logic get its name? People in mathematics. George Boole, figure 2.13. Boole's algebra of logic was foundational in the design of digital computer circuits. Credit. George Boole was born in Lincolnshire, England in 1815. He was the son of a cobbler who provided him some initial education, but Boole was mostly self-taught. He began teaching at 16 years of age and opened his own school at the age of 20. In 1849, at the age of 34, he was appointed professor of mathematics at Queen's College in Cork, Ireland. In 1853, he published the paper, An Investigation of the Laws of Thought, on which are founded the mathematical theories of logic and probabilities, which is the treatise that the field of Boolean algebra and digital circuitry was built on. Reference goes to
you and I, we were meant to be.
Chapter 1, example 137.
I feel it in my soul. Feel it in my soul.
Is analogous to negation.
Never separated you and me. Broken made whole. Broken made whole.
The negation of P and Q.
The world that tries to steal our hope
Not P or not Q. De Morgan's law for the negation.
tries to make us numb, but our love has overcome. And you, my dear,
The negation of a conditional, so the negation of P then Q is equivalent to P and not Q. Writing conditional as a disjunction, you have P then Q is equivalent to not P or Q. Symbols for logical equivalence is the three lines. De Morgan's law allows us to write the negation of conjunctions and disjunctions without using the phrase. It is not the case that ... to indicate the parentheses. Avoiding this phrase often results in a written or verbal statement that is clearer or easier to understand. Example 2.26. Applying De Morgan's law for negation of conjunctions and disjunctions. Write the negation of each statement in words without using the phrase, it is not the case that. 1. Kristen is a biomedical engineer and Thomas is a chemical engineer. 2. A person had cake or they had ice cream. Solution. 1. Kristen is a biomedical engineer and Thomas is a chemical engineer has the form P and Q, where P is the statement, Kristen is a biomedical engineer, and Q is the statement, Thomas is a chemical engineer. By De Morgan's law, the negation of the conjunction, not P and Q, is logically equivalent to not P or not Q. Not P is Kristen is not a biomedical engineer, and not Q is Thomas is not a chemical engineer. By De Morgan's law, the solution was the form not P or not Q. So the answer is Kristen is not a biomedical engineer or Tom is not a chemical engineer. 2. A person had cake or they had ice cream. P is the statement, a person had cake, and Q is the statement, a person had ice cream. By De Morgan's law for the negations of the disjunction, not P or Q is equivalent to not P and not Q. The solution to this is the person did not have cake and they did not have ice cream. Your turn 2.26. Write the negation of each statement in words without using the phrase. It is not the case that 1. Jackie played softball or she ran track. 2. Brandon studied for his certification exam and he passed his exam. Negation of a conditional statement. The negation of any statement has the opposite truth values of the original statement. The negation of a conditional, not P then Q, is a conjunction of P and not Q, which is P and not Q. Consider the truth table below for the negation of the conditional. So we have P, true, 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 false, false, Q, true, false, P then Q, true, true, not P then Q, false, false. The only time the negation of the conditional statement is true is when P is true and Q is false. This means that tilde parentheses P right Q close is logically equivalent to P up tilde Q, as the following truth table demonstrates. So P, true, false, Q, true, false, P then Q, true, true, not P then Q, false, false, not Q, false, true, P and not Q, false, false, so not P then Q, if and only if P and not Q, true. Bam! Constructing the negation of a conditional statement. Write the negation of each conditional statement. 1. If Adele won a Grammy, then she is a singer. 2. If Henrik Lundqvist played professional hockey, then he did not win the Stanley Cup. Solution. 1. The negation of the conditional statement, P then Q, is the statement P and not Q. The hypothesis of the conditional statement is P, Adele won a Grammy, and the conclusion of the conditional statement is Q, Adele is a singer. The negation of the conclusion, not Q, is the statement she is not a singer. Therefore, the answer is P and not Q. Adele won a Grammy, and she is not a singer. 2. The hypothesis is P. Henrik Lundqvist played professional hockey, and the conclusion of the conditional statement is Q. He did not win the Stanley Cup. The negation of Q is the statement he won the Stanley Cup. The negation of the conditional statement is equal to P and not Q. Henrik Lundqvist played professional hockey, and he won the Stanley Cup. Your turn 2.27. Write the negation of each conditional statement. 1. If Edna Mode makes a new superhero costume, then it will not include a cape. 2. If I had pancakes for breakfast, then I used maple syrup. Example 2.28. Constructing the negation of a conditional statement with quantifiers. Write the negation of each conditional statement. 1. If all cats purr, then my partner's cat purrs. 2. If a penguin is a bird, then some birds do not fly. Solution. 1. The negation of the conditional statement P then Q is the statement P and not Q. The hypothesis of the conditional statement is P, all cats purr, and the conclusion of the conditional statement is Q, my partner's cat purrs. The negation of the conclusion is Q is the statement my partner's cat does not purr. Therefore, the answer P and not Q, all cats purr, but my partner's cat does not purr. 2. The hypothesis is P. And the conclusion of the conditional statement is Q. Some birds do not fly. The negation of Q is the statement all birds fly. Therefore, the negation of the conditional statement is equal to P and not Q. A penguin is a bird and all birds fly. Your turn 2.28. Write the negation of each conditional statement. 1. If some people like ice cream, then ice cream makers will make a profit. 2. If Raquel cannot play video games, then nobody will play video games. Many of the properties that hold true for number systems and sets also hold true for logical statements. The following table summarizes some of the most useful properties for analyzing and constructing logical arguments. These properties can be verified using a truth table. So property is commutation. So P and Q is logically equivalent to Q and P. And then also P or Q is logically equivalent to Q or P. Oh, excuse me. Association. close is logically equivalent to parentheses P down Q close up parentheses P down R close. Then De Morgan's rules, the negation of P up Q is logically equivalent to not P down not Q. Negation of P or Q is logically equivalent to not P and not Q. And then for the conditional, the negation of P then Q is logically equivalent to P and not Q. And then P and Q is logically equivalent to not P or Q. Example 2.29. Negating a conditional statement with a conjunction or disjunction. Write the negation of each conditional statement applying to Morgan's Law. 1. If Mom needs to buy chips, then Mike had friends over and Bob was hungry. 2. If Juan had pizza or Chris had wings, then Dad watched the game. Solution. 1. The conditional has the form if P, then Q or R, where P is Mom needs to buy chips, Q is Mike had friends over, and R is Bob was hungry. The negation of P then Q and R is P and not Q and R. Applying De Morgan's Law to the statement not Q and R, the result is not Q or not R. So our conditional statement becomes P and not Q or not R. By the distributive property for conjunction over disjunction, this statement is equivalent to P and not Q or P and not R. Translating the statement P and not Q or P and not R into words, the solution is Mom needs to buy chips and Mike did not have friends over, or Mom needs to buy chips and Bob was not hungry. 2. The conditional has the form if P or Q then R, where P is Juan had pizza, Q is Chris had wings, and R is Dad watched the game. The negation of P or Q is the negation of P or Q then R is P or Q and not R. By the distributive property or for disjunction over conjunction, the statement is equivalent to P or not R and Q or not R. Translating the statement P or not R and Q or not R into words, the solution is Juan had pizza or Dad did not watch the game, and Chris had wings or Dad did not watch the game. Your turn 2.29. Write the negation of each conditional statement applying to Morgan's Law. 1. If Eric needs to replace the light bulb, then Marcus left the light on all night or Dan broke the bulb. 2. If Trenton went to school and Regina went to work, then Merica cleans the house. Merica. Evaluating De Morgan's laws with truth tables. In Chapter 1, you learned that you could prove the validity of De Morgan's laws using Venn diagrams. Truth tables can also be used to prove that two statements are logically equivalent. If two statements are logically equivalent, you can use the form of the statement that is clearer or more persuasive when constructing a logical argument. The next example will prove the validity of one of De Morgan's laws using a truth table. The same procedure can be applied to any two logical statements that you believe are equivalent. If the last column of the truth table is a tautology, then the two statements are logically equivalent. Example 2.30. Verify De Morgan's law for negation of the conjunction. Construct a truth table to verify De Morgan's law for the negation of the conjunction. The negation of P and Q is logically equivalent to not P or not Q is valid. Solution. Step 1. To verify any logical equivalence, you must first replace the logical equivalence symbol, the 3 lines, with the biconditional symbol, left, right. The statement, negation P and Q, logically equivalent to not P or not Q, becomes negation of P and Q if and only if not P or not Q. Step 2. Next, you create a truth table for the statement. Because we have two basic statements, P and Q, the truth table will have 4 rows to account for all possible outcomes. The columns will be P, Q, not Q, P and Q, negation of P and Q, not P or not Q. And the biconditional statement is negation P and Q if and only if not P or not Q. So P, true, true, false, false, true, false, true, false, true, false, false, false. Sorry, P, true, true, false, false, Q, true, false, P and Q, true, false, 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 negation of P and Q, false, true, 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 not P, false, false, true, true, not Q, false, true, not P or not Q, false, true, true, true. And then finally, negation P and Q if and only if, not P or not Q, true, 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 true. Step 3, finally verify that the statement is valid by confirming it is a tautology. In this instance, the last column is all true. Therefore, the statement is valid and De Morgan's law for the negation of a conjunction is verified. One, construct a truth table to verify De Morgan's law for the negation of a disjunction. Negation of P or Q is logically equivalent to not P and not Q is valid.